You ever look at a massive skyscraper and just wonder how it doesn't fall down? It's not magic, it's pure engineering genius. And today, we're going to decode that genius, from a single simple beam all the way to a massive superstructure. You ready? Let's get into it.
All right, let's kick things off with a question that seems almost too simple. Why isn't a steel beam just a big, solid block of metal? I mean, that sounds strong, right? More metal, more strength? But nope. The answer actually reveals the secret key to all of structural design: efficiency. We're about to see why shape, believe it or not, is way more important than just raw size.
Okay, so here's our game plan. First, we'll uncover why steel even has those specific shapes. Then, we'll get to know the essential building blocks, kind of like a steel Lego set. After that, we'll see how they all connect, what forces are trying to tear them down, and finally, how all this comes together to create some truly epic structures.
All right, section 1. Back to our big question, why not a solid block? Well, it all boils down to one word: efficiency. How do you get the maximum possible strength using the absolute minimum amount of material? The answer is a shape you've definitely seen everywhere: the I-beam.
So here's the big secret, the science behind it all. It's called moment of inertia. Now that sounds super technical, I know, but trust me, you already get this instinctively. Just picture a plastic ruler. If you try to bend it the flat way, it's super floppy, right? Easy. But now turn that same ruler on its edge and try to bend it. No way! It's suddenly crazy strong. That's it. That's moment of inertia. All you're doing is moving the material as far away from the center line as possible, and that makes it ridiculously resistant to bending.
Okay, time for a little pop quiz to see if you're with me. In a classic I-beam, which part is doing the real heavy lifting against that bending force? Is it the web, the flanges, the bolts, or the stiffeners? Go ahead and pause if you want to think it over. Got an answer? It's B, the flanges, the top and bottom parts. Just like our ruler, they're the material that's furthest from the center. They're taking all the tension and compression. That skinny piece in the middle, the web, its only job is to hold the flanges apart. So simple, but absolutely brilliant.
So, the I-beam is definitely the main character, but every star needs a great supporting cast, right? And that's what we're talking about now. Honestly, you can think about steel construction as just a massive Lego set. There are only a handful of essential pieces, but with them, you can build practically anything.
And here it is again, our old friend, the I-beam. This thing is the absolute workhorse of construction. Seriously, next time you're in a parking garage or an unfinished building, just look up. You will see these guys everywhere, holding up the floors. Their one mission in life: to carry a heavy load over a long span.
Next up, we have channels, or C-sections. If the I-beam is the star, these are the indispensable backup singers. You see them a lot as purlins in a roof. They're basically the smaller beams that the actual roof panels get attached to. They take the load from the roof and pass it along to the big guys.
All right, another quick check. That purlin I just mentioned, what's its job? Is it connecting the foundation, carrying the roof, supporting walls, or holding a crane? Well, as we just talked about, the answer is B. It's the middleman taking the load from the roof sheeting, rain, snow, all that stuff, and handing it off to the main rafters. A small part, but you can't build a roof without it.
Now, this might look simple, but don't underestimate the humble angle, or L-section. This little guy is the absolute key to building trusses. You know those big crisscrossing patterns you see on old railway bridges or massive electrical towers? That's all built from these. Why? Because they let you easily build triangles, and the triangle is, hands down, the strongest, most rigid shape in all of engineering.
And finally, let's talk about the modern favorite: hollow sections. Square, rectangular, circular, they're all just tubes, but they have a superpower. They're incredible at resisting torsion. Torsion is just a fancy word for a twisting force. Think about wringing out a wet towel. Hollow sections handle that like a champ. That strength, plus their super clean, minimalist look, is exactly why you see them all over modern high-tech architecture.
Okay, so why are these hollow tubes so popular for columns specifically? Let's think about it. Is it price, strength, paintability, or weight? The correct answer is B. It's all about strength. See, a column could get pushed to stress from any direction, right? A tube is perfectly symmetrical. It's equally strong no matter which way you push on it, which makes it fantastic at resisting buckling. Plus, like we said, it's great with twisting forces.
Okay, so we've got our Lego pieces. We know what they do, but now for the most important part. How do you stick them together? And this is where everything gets, well, critical. You've heard the saying, a chain is only as strong as its weakest link. In buildings, the joint is always the weakest link.
So in the modern world, it really comes down to two main options: bolting or welding. Bolting is kind of like building IKEA furniture.
It's fast, it's pretty easy to do on site, and it's perfect for prefabricated buildings that are assembled like a kit. You can even take it apart later. Welding, on the other hand, that's more like performing surgery. You're literally melting the two pieces of metal until they flow together and become one single piece. The result is an unbelievably strong bond, but man, it requires a huge amount of skill and careful inspection.
Quick quiz time again. Between bolting and welding, what's the #1 advantage of welding? Take a look. The answer is C. It creates a rigid, monolithic joint. Monolithic just means like a single stone. The connection is so complete that the two separate pieces now behave as if they were always one solid piece of steel. And that extra rigidity can be absolutely critical for certain designs.
All right, this next part is really cool, because great engineering isn't just about building things up. It's about thinking through all the ways they could fall down. It's about designing for failure. Every single steel structure is in a constant battle against three great enemies. First up, enemy number one is buckling. If you take a long, skinny piece of steel and compress it, it doesn't just neatly squish down. It suddenly and catastrophically bends sideways and snaps. Think about crushing an empty soda can. That's buckling. Enemy number two is corrosion. You know it as rust. It's a silent killer, slowly, year after year, just eating away the material. And finally, enemy number three, fire. Now, you might be thinking, wait, steel doesn't burn. And you're right, it doesn't. But it has an Achilles heel. At 550 degrees Celsius, steel loses 50% of its strength. It basically turns into wet spaghetti. And when that happens, a building can collapse. This is exactly why structural steel is always coated in that thick, bumpy, fireproofing material. It's not to save the steel, it's to buy precious time for people to escape.
Okay, last quiz question, and it's an important one. What's that critical temperature where steel starts to fail? I hope you remember, it's C, 550 degrees Celsius. I promise you, every single structural engineer on the planet has that number burned into their brain.
So let's recap. We've got our efficient shapes, we know how to connect them, and we know what we're fighting against. So what happens when you combine all of that knowledge? Well, you can create a true masterpiece of engineering. You get something like the space frame.
So what is a space frame, and why is it so cool? Just look at it. It's basically a truss, but in 3 dimensions. It's this incredible lattice of interconnected triangles. And its genius is that instead of forcing the load down a few big, heavy beams, it shares the load. It distributes it throughout the entire structure in all 3 dimensions. It's like a team effort. And that's how you get these massive, column-free spaces you see in convention centers, airport terminals, or stadiums like the DDA Siri-Fort Sports Complex. It's this beautiful combination of being unbelievably strong and rigid, while also being incredibly lightweight. And really, that's the whole secret. The genius of steel design isn't one complicated thing. It's a handful of simple, elegant rules that, when you put them all together, literally build the modern world. So my challenge to you is this. The next time you walk into a big building, a train station, or walk under a bridge, just look up. I bet you'll start seeing it all differently. You'll spot the I-beams, the trusses, maybe even a space frame, because now you know the language. You know the secrets holding it all together.